Hello. Today we are going to start about public key cryptography. We have discussed several times that the difference between symmetric key cryptography and public key cryptography is that in symmetric key cryptography we use the same key for encryption and decryption, where in public key cryptography we have the separate two keys for encryption, which is different from the decryption key. So this is going to be the first lecture about public key cryptography. So in this lecture we discuss about primality tests and RSA encryption scheme. So when we in our previous lecture also I explained or just mentioned you that in public key cryptography we have to rely on mathematics very much. So public key cryptography is very heavy in mathematics, about specifically discrete mathematics. The topics we discussed earlier, the symmetric key topics like block ciphers, the stream ciphers, and historical ciphers, those things we don't have very much mathematics there. We just have some concepts like substitution, uh, shuffling, likewise, and and XORing, that sort of operations. But here, public key cryptography is heavy in mathematics. Therefore, generally we can say like encryption and decryption processes are itself very heavy. Heavy means like computationally costly. So significant computation power should be there, and also some memory should be there. So they are not efficient as symmetric key cryptographic operations. So therefore, in most of our day-to-day applications, data encryption is taken place using symmetric key cryptographic algorithms for like vast communications. But public key cryptography is used for places like to share secrets or generate signatures, that sort of one-time operations. But after that, once the secret is shared, then using that secret derive a key and use symmetric key cryptography for normal data encryption for the communication purpose. So that's a kind of a general discussion about public key cryptography. So let's start about number theory in cryptography in very brief. So most prominent public key cryptography systems use large prime numbers. So when we talk about public key cryptography, we are often talk about prime numbers. Prime numbers play a very prominent role in public key cryptography. So generating large prime is easy. We need to be able to do this often. So we have to generate or choose large prime numbers, and we are playing tricks with them. That's how we do public key encryption and other operations. And also in cryptography, so this is like in public key cryptography we have to rely on like we can say like, since this problem is hard to solve mathematical problem, because of that property we are going to say our crypto system is secure. So our crypto system is not easy to break. So likewise, that means I would say like we reduce the security of our often we reduce the security of our public key encryption or signature or whatever public key crypto systems to some hard mathematical problem. So we rely on the difficulty in solving that mathematical problems using our computational systems. So you will understand it when you get familiar with these terminologies and concepts. So basically, I have to say, like, public key cryptography really depends on mathematics, and the hardness like the limits we have there is like we are we are saying like the possibility or the hardness of our breaking our crypto system is relying on the hardness of solving a particular mathematical problem. If that problem is hard to solve, we can say it is difficult to break our crypto system. Likewise. Okay, so factorizing seems to be hard, or at least not easy. There, that means using currently available algorithms, it is not easy to do the factorization. Factorization means like when a number is given, we have to factorize that number to parts. So in our public key cryptography, we mostly rely on prime number. So this factorization is once a number is given, the task is to factorize that number as a product of prime numbers. So we say according to like the by using currently available algorithms or computational systems or the computational powers, it is difficult, it is not easy to factorize a number to prime numbers. So recall that a number which has no factors apart from 1 and itself is called a prime. You know what is a prime number. So that's the definition of the prime number. A number which has no factors apart from 1 and itself. A number which is not prime is called composite number. So 2 is a composite number, 3 is a prime number, 4 is a composite number, 5 is a prime number, likewise. In public key cryptography, we talk about prime numbers very much, and also we rely on hardness assumptions like factorizing is a hard problem, or exponentiation is hard, something like that. Okay, so because we talked about prime numbers, I would like to give you some insight uh, about these prime numbers, and I'm, I don't need I don't want you to memorize all this stuff, but it is very important to understand the concepts if you are really interested in cryptography. Okay, testing for primality. Testing for primality by trivial is not practical except for very small numbers. I think you can understand. We can, once a number is given, we can easily identify whether the number is a prime or composite if the number is a small number. But for very large numbers, it is difficult to find whether the number is prime or composite. So, for example, if the number is 3, we can find whether it is a prime or composite. 5, 7, likewise. So 10, 15, we can find whether we can have prime factors or whether it is a prime number itself. But for very large numbers, let's say like numbers with 10, 15 digits, that is not possible. That is not possible. Oh, nearly hard, very hard maybe. So there are a number of fast methods which are probabilistic. They require random input and can fail in exceptional circumstances. And when we talk about cryptography, this term probabilistic is very often used. So these are kind of kind of advanced stuff, but I would like to expose you to the terminologies we use in cryptography. So I hope that will helpful for you. So probabilistic means, what is probabilistic? We have discussed that thing as well in our previous lectures. Probabilistic means once a task is given, we cannot have exact idea about the output. It can happen or not. It can be successful or not. There is a small chance for a failure. That's what we call probabilistic. Deterministic is the opposite of probabilistic. That means when the problem is given, we have exact idea about the output. We know output is this. We can find. So, for example, let's say like addition of two numbers, 2 and 3. The output is deterministic. It's 5, always 5. But some other case, like if you toss a coin, the output is probabilistic. It can be head or tail. There's a chance. That's what we call probabilistic and deterministic. So in the methods we have for testing the primality, there are fast methods, but they are probabilistic. Sometimes we can find whether the number is prime or not. Sometimes there is a failure. We cannot get the exact answer. So that's why we call they are probabilistic. So in 2002, 3 Indian mathematicians, Agrawal, Saxena, and Kayal, found a polynomial time deterministic primality test. What is polynomial time? In cryptography and theoretical computer science, we often use this term, polynomial time. Polynomial time means, for example, like in very simple words, polynomial time means something we can solve or do within using our existing computation powers, and given a time we can find like within a given time period. That is polynomial time. But the other thing is we have exponential time. Exponential time means if we say like solution can be found in exponential time, so we do not consider that as an efficient solution for the problem. It takes huge time. So when the input is going to be uh, increased, the time taken for the solution is going to be exponentially high. So that means it is not efficient. So in theoretical computer science and also cryptography, we focus polynomial time algorithms. If the algorithm is polynomial time, then we can accept that it is efficient algorithm to solve our problem in a reasonable time period. And deterministic means, okay, there's a chance for the failure. So in 2002, 3 Indian mathematicians found a polynomial time deterministic primality test. So polynomial time means, okay, we can accept that as an efficient solution for finding prime numbers. And deterministic means there is a chance for a failure. Although a huge theoretical breakthrough, the probabilistic methods are still used. Sorry, deterministic means like there's no chance for failure. We can accept answer. Sorry for that. So deterministic means once the problem is given, we can exactly get the solution. Probabilistic means there's a chance for a failure. So although this finding is a huge theoretical breakthrough, we still use probabilistic methods in practical case because of their efficiency, because they are polynomial time, something like that. So we examine one of the simplest test for Fermat, the test for finding prime numbers, which is called Fermat Primality Test. I'm not going to talk about that in very detail, but for the time being, keep in mind. If you like, you can follow these slides and understand. But for the time being, keep in mind there are tests for find whether a number is a prime number or not. One test is Fermat test, and then we can, using that sort of tests, we can find, given a number, we can find whether the number is a prime number or a composite number. In cryptography, or in most cases in theoretical computer science, prime numbers are very much useful. So there should be algorithms to find prime numbers. In cryptography, especially, we need to find very large prime numbers. So there should be a way to find, efficient way to find large prime numbers. So this Fermat primality test is one simplest test for find whether a number is a prime or not, and this is a deterministic. This is a probabilistic test. You can follow this slide and understand it. I'm not going to talk about that in detail. For the time being, keep in mind this is a test to find whether the number is a prime or not. And in our next slides, you will understand the use of prime numbers when we talk about the RSA crypto system. And these are few facts about effectiveness of the Fermat test. So it says if the test outputs composite, if we test a number for a prime or not, let's say like the test outputs the number is a composite number, then the number is definitely a composite number. Do you understand that? It is said like I said, this Fermat test is a probabilistic uh, test or probabilistic algorithm to find primality of a number. So using that Fermat test, if we test a primality of a number and we get an output as a composite, then the number is definitely a composite. But if we can get output as a prime, there is a possibility that number may not be a prime. So that's the chance of failure. So that's why we say this test is a probabilistic test. There is a probability that if it say it is a prime number, there's a possibility that that number is not a prime number. So test can output a probable prime if n is composite. So it can say it's a prime, but there is a possibility that number is not really a prime. So because of that, we say it's a probable prime. There's a chance that it is not a prime number. But if it says the number is a composite number, it's definitely a composite. So probable prime, that's why we say it is pseudo prime. It can be a prime, but not a real prime. It can be a real prime or not a real prime. So there are some composite numbers for which the test will always output a probable prime. That those numbers are called Carmichael numbers. So Carmichael is the person who found that there is a chance of getting probable primes using this test. So these are the Carmichael numbers: 561, 1105, likewise. So these are Carmichael numbers. That means if we test these numbers using the Fermat primality test, it always says the number is a prime number. So since we know that these numbers are not really prime, we say they are probable prime. The algorithm outputs a probable prime, but they are not really prime numbers. Okay. And the other test is Miller-Rabin test. So these are the people who generated or found this algorithm, uh, this primality test. So this is same as the very similar idea as the Fermat test. You can follow the slides and understand the test, how it works. And that's about prime numbers. So why we are so much interested in prime numbers? That's because we need to find prime numbers, large prime numbers, to be used in cryptography. That's why we are so much interested in how to find large prime numbers. Check the number, and then we can say, okay, this is a prime number, and then we can use that number for our cryptographic purposes. Okay, that's about prime numbers and primality tests in mathematics. So that is useful for cryptography. And then we talk about integer factorization. Factorization by trivial division is an exponential time algorithm and is hopeless for numbers of a few hundred bits. So for example, like let's say, like in other words, fact I mentioned that factorization is when a number is given, factorization is to uh, factorize the number, or like divide this number for prime factors. So for example, if 15 is given, factorization of 15 is going to be 3 and 5, two prime factors. Likewise, so factorization by trivial and exponential time algorithm. Exponential time algorithm I mentioned, if an algorithm is exponential time, we consider it is not an efficient algorithm for computers. We cannot use we cannot efficiently use computers to solve the problems. So that means if 15 is given, we can easily find two prime factors. But let's say a number of 100 digits is given, this is going to be like 1,000 years to solve the problem. So exponential time, the when the numbers are smaller, time is smaller, but numbers are getting bigger, the input size is going to be bigger. This is exponentially growing. The solving time is going to be exponentially growing. So it is hopeless for numbers for few hundred bits. A number of special purpose methods exist which apply if integer to be factorized has special properties. The best current general method is known as the number field sieve. So this is the best currently available, currently known method for factorize a number, but this is sub-exponential time algorithm. Sub-exponential time algorithm means this is not really exponential, but not efficient as what is other called polynomial time. This is not efficient as polynomial time, but not going to be inefficient as exponential, in between, sub-exponential. That's the best known solution to factorize integers. So in theoretical computer science, if we have polynomial time algorithms, we say, okay, they are efficient solutions. If they are exponential time algorithms, they are not efficient for real usage. But sub-exponential time algorithms, we can we can take them as kind of little bit efficient ways of solving the problems, but they are not really efficient. Okay, these are some factorization records. if we have a number with decimal digits 140 or 160, according to March 2002, this will take CPU years 2.7. So the CPU years assume 1 gigahertz CPU. Using 1 gigahertz CPU, we have to spend 2.7 years to factorize this size number. If the number is going to be 232 decimal digits, according to 2009 December, it is going to be a CPU years 3300. So now we can understand that factorizing bigger numbers is going to be very difficult task, very inefficient according to the currently available algorithms like number field sieve algorithm. That's the currently known best algorithm. Using that, this is the facts we can get. And this is some information about brute force key search and factorization. So for example, if we have symmetric key length 80 symmetric key, doing a brute force for this key length is similar to factorize a number of this much, 1024. This means example brute force search of 128-bit keys for AES roughly same as computational effort as factorization of 3072-bit number with two factors of roughly equal sizes. So that means we can say having a AES algorithm with 128 bits key size is kind of equivalent to having a RSA algorithm of 3072 size n. N is a value we compute there. We will discuss about that. This is some kind of a comparison between symmetric key brute force for symmetric key length versus factorizing a number, factorizing numbers, comparing with their sizes. Okay, now we are going to talk about our real topic, that is RSA crypto system. So to come to that point, we discuss several other things. You might feel it is a little bit boring, but try to understand. We discussed so much about prime numbers, integer factorization, and different kinds of like exponential algorithms, sub-exponential, polynomial time, that sort of terminologies, because they are very useful for cryptography. And really, the prime numbers are very useful for cryptography. That's why we talked about how to, the methods about finding whether the number is a prime or not. Okay, so RSA is probably the best known public key crypto system. It is widely deployed in many kinds of applications in our day-to-day internet. We use RSA for encryption, for signatures, for secret, like sharing secret keys. For many purposes, RSA crypto system is used in our day-to-day internet. That means this is deployed in TLS SSL protocol suite, which is used when we use HTTPS. The basic equations are simple, but in order to achieve security, we must be careful about some kind of pre-processing. Pre-processing means before doing the encryption, we have to do some kind of processing for the input, for the message. In AES, we discussed about some kind of pre-processing, that is like adding some padding schemes, padded values, dividing blocks likewise. So similar things are done in RSA system to make it secure. If implemented in a standard way, there are no known attacks on RSA encryption. So until now, there are no known attacks. This is introduced in 1976 or something. For more than 40 years, we don't have known attacks for this RSA crypto system. It is very simple. Okay. So this is introduced or invented by three cryptographers: Ronald Rivers, Adi Shamir, and Michael Adleman. Uh, so two American cryptographers, Rivers and Adleman, and Shamir is Israeli cryptographer. So they invented this in 1977 at MIT. So this picture is old picture. By the time they discovered this one, they invented this scheme. They were young at that time. Now you can find pictures of them. They all are old with gray hair and baldy heads. And this is a public encrypted system and digital signature scheme. So we can use this for two purposes: to encryption and signature. And this is based on integer factorization problem. We discussed that integer factorization is very hard. We don't have any known efficient algorithm for this. The only efficient algorithm we have is number field sieve algorithm, but it is sub-exponential algorithm. It is not possible to efficiently solve the factorization problem. This cryptographic scheme, RSA, is based on integer factorization. That means if integer factorization is going to be hard, it is hard to break the crypto system RSA. That's how we can reduce the security of RSA system to a problem. That statement says that. So this, since the RSA crypto system is based on integer factorization problem as the underlying mathematical problem, once this underlying mathematical problem is hard, it is hard to solve or break the RSA crypto system. So RSA patent expired in 2000. I don't know about information about that. Okay. So RSA key generation. This is you have to understand this clearly. So let P and Q be distinct prime numbers randomly chosen from set of all prime numbers of certain size. You can say size of 100 digits or 124 digit number. So bigger size, 124 digits or 1024 digits or 2048 digits. Likewise, you can give a size for the pool of numbers, and from that you choose two prime numbers randomly, P and Q. So for this purpose, to choose the prime numbers, you have to check whether the number is a prime or not. For that purpose, you use primality test. Okay, once you have two prime numbers randomly chosen from a pool of certain size numbers, and important word is there, distinct prime numbers. Distinct prime numbers is P and Q are different. P is different number, Q is a different number. They are not going to be same. So once we choose, let's say 3 from the pool, we cannot choose 3 again. 3 and another number, except 3 and any other prime like that. And then compute n, which is the product of P and Q. And then randomly select e value with GCD, greatest common divisor of P and Pn is 1. So this means E and Pn are relatively prime numbers. Relatively prime. There are no common divisors for them. So how to compute Pn? I think you can follow the slides I have given you at the beginning of the series about basic mathematics, and then you can find how to find this Pn. In the case of n equals P and Q, where the P and Q are two prime numbers, Pn is P minus 1 times Q minus 1. For other kind of numbers, there are other ways. In this case, if the number n is going to be a product of two prime numbers, this is going to be P minus 1 times Q minus 1. Okay. And GCD of the greatest common divisor of these two numbers are going to be 1. That means two numbers are E and N are going to be relatively prime. And then compute D in a way that it is equal to inverse of E mod Pn. I expect you to do these kind of mathematics because I have uploaded some lecture slides, and also you have done this kind of things in your basic mathematical courses. I expect you understand how to compute these things. And once we have computed the thing at number 4, then the public key is the pair of N and E. So E is going to be a parameter in the public key, and N is going to be a parameter in the public key. The private key consists of P, Q, and D. These three values, P, Q, and D. See here, N equals P and Q, but but we keep N as a public key, and we keep P and Q as secret keys. According to the concept of factorization problem, the hardness of factorization problem, once N is given, it is hard or nearly impossible to factorize N into P and Q. So this is kind of a one-way function. We can find P and Q and compute N, but given N, it is hard to compute P and Q, factorize it into P and Q. Okay, this is how the key generation is taken place in RSA algorithm, and this is how the RSA do the encryption and decryption. So the public key encryption, public key for encryption is N and E. I told you in the previous slide. So input in any value M, which is going to be within the size of 0 to N. How we compute the encryption is M, the message value, to the power E mod N. So we often use this C equals E in brackets M comma KE as the notation for encryption, not only for RSA but for any encryption scheme. E means encryption algorithm, or we can use ENC, enc, and inside the brackets we give the parameters we pass. M is the message, KE is the encryption key. So this is a general notation we use. Specifically in RSA, how this encryption operation happens is M to the power E mod N. And for the decryption, C is the ciphertext which is computed here in the encryption. C to the power D mod N, which is going to be M again. Do the reverse. And in this case, note that any message needs to be pre-processed to become the input M. This includes coding as a number and adding some randomness. We discuss about that details later. For the time being, this is how the textbook RSA happens. Encryption is m to the power e mod n. E is the public key value, and n is the public key value as well. And for the decryption, c to the power d mod n. D is the secret key value, which is used only for the decryption. So when we have a public key encryption scheme, the person who owns the public key encryption scheme shares the public key to the other parties who are going to communicate with him. So public key, I share my public key with others. Publicly share it, like keep it in a telephone directory, or keep it in my website, or keep it in stick it as a label in my front door, something like that. So anybody can use that and do the encryption and send the message. Once the encrypted message receives, I use my secret key, the D value. I do not publish that. I keep it for myself. Use that. I do the decryption. Only I can do the decryption, but anybody can do encryption and send messages to me. But only me can decrypt and read the message. Nobody else. So this is the concept of public key encryption. And in this case, we talked about how the encryption and decryption happens in RSA, and we know that here P and Q values are going to be secret, while the N value, the product of P and Q, are product of P and Q is public. Why do we need to keep this P and Q as a secret? Because once P and Q is available, anybody can compute phi n value. Using phi n, E value is public value. Outside world knows that. Once E is known and phi n is known, anybody can find or compute the D value. That's why we have to keep P and Q as secret values. But once N is known, it is hard to factorize it into P and Q. So you can understand N is public, but P and Q is secret. So factorizing N into P and Q is the core part of the security of this crypto system. If it is possible, once the N is given, if it is possible to factorize N into P and Q, that means the security of this RSA crypto system is gone. Anybody can break this. But key point is this computation is hard. So hardness of this factorization is the key part, or the core part of this core part of security of this RSA crypto system. Okay, I think now you can understand why we talk about this the factorization so much when we talk about RSA. So RSA is secure as long as factorization is a hard problem. If factorization is not a hard problem, let's say like there will be an efficient algorithm to do the factorization, then RSA algorithm is no longer secure. By looking at N, anybody can compute D value, because P and Q can be factorized, N can be factorized as P and Q, and using that easy to compute D by knowing E value. E is a public value. Okay. So this is a numerical example of how the encryption and decryption happens in RSA. And I'm not going to talk about the correctness of RSA, which is more heavy in theoretical side. If you like, you can read this and understand. I would like if you read and understand this part. This is kind of a proving the correctness of RSA. Proving means like proving why this encryption goes back to uh, the exact plain text again. That proof. In cryptography, proofs they play a very crucial role in cryptography, because that's the only way we are going to give the evidences of the security and efficiency of our security, correctness and efficiency of our crypto systems. We mathematically prove them. Okay, so I'm not going to discuss any more details for today, and from next lecture we'll discuss the rest of the parts from the slide 19. For the time being, try to read and understand and take a pen and paper and do the calculations and everything, and try to understand this part very clearly. This is very important, very interesting if you are interested in cryptography. And another thing I would like to say, there are no lot of cryptographers in Sri Lanka. We have some security specialists, but they are in application side. They are for network security. They are using tools and firewalls, that sort of things. Hacking is there, but real hacking is happening here. How to break a crypto system is a really a breakthrough. This is like we have to use tools, but we have to really attack the underlying concept. We have to find algorithms. We have to design algorithms, find the weaknesses. So this is very tough and very interesting and highly paid area in IT cryptography. So if you are interested, you can take your time and master these things. So you will have a lot of opportunities for doing higher studies in good places and become cryptographers for highly known places like Google, Facebook, Microsoft, that sort of things, and work for military as well. So if you are interested, try to understand these concepts very clearly, and we'll discuss other rest of the things in our next lecture. Thank you.